All right, today we're going to tackle a question that really gets to the heart of what it means to go from being a computer science student to a practicing engineer. We're going to explore why choosing an algorithm isn't about finding some perfect, best answer, but about making smart, informed trade-offs. We've all been trained to ask this, right? Whether you're sorting data, searching through it, or whatever, this question feels like it's the right one. It sounds sharp, intelligent, and like you're laser-focused on performance.
But here's the twist. In the real world, where you're building actual systems, that question is usually a trap. It's built on this myth that a single best algorithm even exists outside the clean, simple world of a textbook.
And that gets us to the most important point of this whole explainer. We don't just pick an algorithm off a shelf like we're grocery shopping. We have to negotiate with reality. We're constantly balancing an algorithm's strengths against our system's limits, our data's quirks, and what we need to do in the future. This is where theory gives way to engineering.
So here's our game plan. We'll start by totally dismantling this myth of the best. Then we'll look at what algorithms are really competing on. We'll dive into the core trade-offs, why your data is everything, and why you have to see the bigger picture, the whole system. And we'll wrap it all up with what it means to have an engineer's mindset.
Okay, let's get right into it. If it's not just about raw speed, then what is the actual competition all about? What are we judging these algorithms on? Well, take a look at this list. It's about so much more than just speed. Yeah, time complexity is on there, of course, but so is space usage. How much memory does it eat up? And what about predictability? Can I count on this thing to perform consistently, or is it going to surprise me? And then there are the ones that really matter in a team setting. Simplicity and maintainability. Can someone else actually understand and fix this code a year from now? These are the real battlegrounds.
And all of this leads to a fundamental law of system design. There is no free lunch. It's just not a thing. When you optimize for one of these dimensions, you almost always pay a price somewhere else. Make it faster? It probably needs more memory. Make it perfectly optimal? It's probably now terrifyingly complex.
So, let's make this more concrete. We're going to walk through the main axes of negotiation that every single engineer has to navigate. First up, the all-time classic showdown, time versus space. You want to make your application faster? A great way is to use caching. But what is a cache? It's memory. You're literally buying speed with the currency of memory. It is a direct trade-off every single time. And here's a perfect textbook example that actually plays out in the real world. Merge sort gives you this nice, guaranteed, predictable performance. Rock solid. But it has to create copies of your data to do it, which means it uses extra space. Quicksort, on the other hand, can do its magic in place, saving you that precious memory. The catch? Its worst-case performance can be absolutely awful if the data isn't kind to it. So which one do you pick? It depends. How much risk can you tolerate? And that idea of risk leads us straight to our next axis, worst case versus average case performance. If you're building a financial trading system, you simply cannot have an algorithm that might, once in a blue moon, take 100 times longer to run. You have to design for the worst possible day. But for a social media feed, the average speed is all that really matters for the user's experience. The choice you make is dictated by your system's tolerance for risk. Now here's one that gets overlooked in the classroom all the time. Simplicity versus optimality. A super clever, hyper-optimized algorithm might be beautiful on a whiteboard, but if it's so complicated that nobody on your team can figure out how to debug it, it's a liability. It's a ticking time bomb. A simple, correct algorithm that people can actually maintain is almost always more valuable than a fragile, perfect one. And finally, let's talk about theory versus the cold, hard reality of the machine. Big O notation is a fantastic tool, but it's an abstraction. It completely ignores how a modern CPU actually works. Things like cache locality, just keeping the data the CPU needs nearby in memory, can make a theoretically slower algorithm run circles around a faster one in the real world. The metal always matters. Okay, moving on to what is arguably the most important factor in this entire negotiation, the data itself. If the algorithm is the tool, then the data is the material you're actually shaping. See, an algorithm's performance isn't some fixed intrinsic thing. It's a relationship between the code and the data it's chewing on. You have to be a detective. How big is this data going to get? Is it spread out evenly, or is it all clumped up? Is it already partially sorted? How often does it change? Knowing this stuff is totally non-negotiable. I mean, think about it. Everyone learns that quicksort is faster than insertion sort. But if you give them a list that's already almost sorted, insertion sort can be dramatically faster. Or hash tables. They are brilliant for quick lookups, unless an attacker crafts inputs designed to cause collisions, which can grind your entire system to a halt. The data dictates your strategy, period.
So now, it's time to zoom out. Because an algorithm doesn't run in a vacuum. It's just one piece, one gear, inside a much larger and more complicated system.
Your code is just one step in a much longer pipeline. Making your algorithm twice as fast is completely pointless if the system spends 99% of its time just waiting for the network or talking to a slow database. It's like meticulously tuning a race car's engine when the real problem is that you have a flat tire. You have to see the whole track.
And this is what system-level thinking is all about. It's about asking the tough questions that separate a coder from an architect. Where is the actual bottleneck? How is this thing going to behave with 10 million users instead of just 10? When things get crazy, what part of this system is going to crack first? The most brilliant choice for one small part can be an absolute disaster for the whole.
So how do we pull all of this together? Well, it all culminates in a fundamental shift in mindset. A shift away from just memorizing facts and toward exercising professional judgment. An experienced engineer doesn't just ask, what's fastest? They think in scenarios. They're always thinking about the future. They're considering the environment. Are we on a massive server with tons of memory or a tiny little phone? They're weighing probabilities. It's all about situational, contextual judgment.
And that really leads to this critical reframing. An algorithm isn't some rigid recipe that you follow step by step. No, it's a tool in your toolbox. And just like any tool, it's brilliant for some jobs and completely, totally wrong for others.
And this, right here, this is the core of it all. This is the main takeaway. True mastery isn't about memorizing a league table of algorithm speeds. It is the wisdom to look at your specific problem, understand all the competing forces, and then consciously and deliberately choose which sacrifice you are willing to make to get the job done.
So, the next time somebody asks, what's the best algorithm? You'll know the real answer is, it depends. Understanding that dependency and navigating all of those trade-offs, well, that's not the end of your journey with algorithms. It's the very beginning of thinking like an engineer. Thanks for joining me.